right, moving into section 2.6 where we're going to look at some more stuff with functions. This chapter 2 is basically all about functions. So we're going to be looking now at combinations of functions and also another operation that we refer to as the composition of functions. So in section 1.2 we discussed the domain and range of a function, and we worked with fractions to determine what numbers would make the denominator 0, and we kind of excluded those because those were ones that were not allowed to be in our domain. We are going to continue this idea with polynomials, more fractions and radicals. So remember that the domain is the set of all allowable x values. Get my pen going here. All about allowable x values. So the domain will be all real numbers unless there is a function where values need to be excluded. So anytime that you have a polynomial, which this is one down here that we have, there is not any number that you can't do any of those operations on. So for a polynomial function, we will end up having a domain of all real numbers, okay? So our cubes, our squares, anything like that, we will have an all real domain. But the two functions we have to worry about where there is a restriction is our fraction functions, which we call rational functions, and our square root functions. So to find the domain of a rational function, we need to exclude the numbers which make the denominator equal to 0, and we've seen some of those already, and we will work with more of those. Now, for a square root function, when we're talking about graphing and stuff in the real numbers, a square root function, I could take the square root of like the square root of 36, the square root of 32, the square root of 79, all of that kind of stuff, but I cannot take the square root of -4 in the real numbers. So remember that we have to have some positive numbers underneath that square root in order for us to have something that we work with in the real numbers. Now remember, this is imaginary, but when we're working in the real numbers, for our domain, we want to allow only numbers which make the radicand greater than or equal to 0. Okay, so it can be 0, but I can't have a negative number. Now remember, the radicand is what's underneath the square root. Okay, now we want to look at these functions and find the domain and write our answers in interval notation. So I just alluded to that polynomial. This is a polynomial function. So there's not any number that I can't square that I add twice of that number and subtract 5. No matter how pretty or how nasty it is, we can do that for every single number. So in interval notation, the way that we write all real numbers is from -infinity to +infinity with that interval notation. Okay, then we turn to the case where I have a fraction. So up here, this is our rational functions where we have to exclude the numbers that make the denominator equal to 0. So if I look at what's in the denominator, there's a possibility that we could get 0. This is a polynomial. Anytime you have something with a higher power than 1, you want to try to factor what's in the bottom so that you can easily see what makes that equal to 0. That's the reason why we practice some of that factoring. So with that trinomial, it's going to factor into two binomials, and so I have a last sign of a minus, so they are different. So I'm going to do a plus and a minus. I'm going to split my x squared up as x and x, and because I have that nice 1 in front, what do we multiply to get 12? That I subtract to get a 1. Well, factors of 12 are 1 and 12, 2 and 6, 3 and 4. If I subtract all those, these are the two that I want, that when I subtract to get a 1. Now I need a positive 1. So I need a +4 and a -3. So now we ask ourselves, what makes this equal to 0? What makes this equal to 0? So I cannot make or have in my domain what makes this 0 and what makes this 0. Well, this would be -4, and this is going to equal 3. Now, before when we did this, I believe we wrote our answers like this, where we said x cannot equal -4, x cannot equal 3. But in interval notation, I have to pick up out of those, okay? So starting at -infinity, I'm allowed to go to -infinity until I get to -4. Then I have to union and skip over that. Remember, we're not including -4, so I have to have a parentheses. Then I'm going to skip over from -4 to 3 all those numbers in between there, then I'm going to union everything else from 3 to infinity. So it looks kind of strange, but numerically on a number line, this is what we were doing. If this is -4 and this is 3, I have to exclude this and exclude that. So I want all of these numbers that matches with that interval, then all of these numbers matches with this interval, and all of these numbers now match with that interval. Okay, so if you have to draw a graph or something to get your interval notation like that, please do so. So this would be our final answer in interval notation. It's kind of big, but that's what it is. All right, let's look at this one with our square root function. With the square root function coming back up here, remember, our allowable values that we can square root underneath there are only positive. So what we have underneath here has to be greater than or equal to 0 for it to be even a case that we can do in the real numbers. So what you want to do is take the radicand and set up an inequality where we're greater than or equal to 0 and solve it. So if I set x minus 5 greater than or equal to 0, then I can solve this inequality by adding 5 to both sides, and I get x to be greater than or equal to 5. Now, that graphically equal to, we had a bracket, and greater than or equal to 5 then ends up being all of these numbers. So if I want to write this in interval notation, I can equal 5. So I need a bracket starting at 5 going to positive infinity. Parenthesis, always around an infinity. This is your final answer. Okay, and the last little one that you will see will be combining this second example and this third example together, which is actually a rational function that has a square root in the bottom. So if we combine the two, starting with our radical, remember what's underneath here has to be greater than or equal to 0, but if this was equal to 0 in this case, the square root of 0 is 0, and I would have 1 over 0, and that's a problem. So anytime you combine, so maybe I add a third one here. Let me erase this real quick. Maybe we add a third one here and say a combo of 1 and 2, we're going to take the radicand, and instead of being greater than or equal to 0 this time, we have to take the equal to part. So basically, we're just going to take the radicand and set it greater than 0. And that's going to give us our domain. So in this case, I want to look at where x plus 3 is positive or greater than 0, and that is going to be all the numbers that we can allow to be in there. Anything other than that would make that an undefined answer in the real numbers. So when I subtract 3 from both sides, I get x to be greater than -3. And so, graphically, again, this might help some of us out to graph it. If I'm at -3, I'm not equal at -3, so there'd be a parenthesis, and greater than would be in this direction. So I'm going to have from -3 to positive infinity, and I'm going to be parentheses on both sides because there is no equality there. Okay? All right, very good. So that is the idea of domain with other functions besides, the polynomial obviously is the easiest, but kind of working with interval notation as well again. All right, moving along, we have talking about algebra functions. So just like we can add, subtract, multiply, and divide expressions or numbers or cases maybe, we can also do that with functions. And that's what we're going to see here with this. So we can combine functions by adding, subtracting, multiplying, and dividing. We're going to let f and g be two functions. Now the sum, which is adding, the difference, the product, and the quotient are functions whose domains are the set of all real numbers common to the domains of both of the functions, defined as follows, okay? So what we're going to do is determine what the function is first, and then they're going to ask us, well, what is the domain for that function? So I'm going to define the sum of two functions, f plus g of x. This is, by definition, the same as taking f of x plus g of x. So basically, you're just going to add the two functions together. Moving down for the difference. If I want the difference, that means I'm going to subtract my two functions. They may give it to you like this, but we're going to operate by just subtracting the two functions together. For the product of two functions, I'm going to go FG, which remember, if there's nothing that you see between those, then it is a product or a multiplication. This means that I'm going to do f of x times g of x. And then our last one with our quotient, if I take f over g of x, then that's the same as taking f of x and dividing it by g of x. Now here, this has a condition where g of x is not equal to 0. Because why? If it was equal to 0, that denominator would be 0, and that is not good. That's bad. Okay? Alright, so here we're given two functions, f and g. And we are going to be asked to find each one. Whoops, that thing didn't get moved over. This is supposed to be the difference. Alright. We want to find each of these operations and then also discuss the domain for each one. Alright, so here's f and here's g. So by definition of f plus g of x, that means that I need to take f of x and add to that g of x. So I'm going to find f of x, which is this x minus 5. So I'm going to do x minus 5. Then I'm going to add to that this guy, which is x squared minus 1. Now this goes back to the idea when we are combining like terms. How do I simplify this? Well, in this case, this plus between these two sets of parentheses does not make a difference, okay? So that means that we're going to end up, I'm going to put some equals here. We're going to end up just combining like terms as much as we can. You could rewrite this without the parentheses if you want, but it's not going to make a difference. So when I combine those like terms, I'm going to get x squared, nothing to go with the x, so I have a plus x, and then I have minus 5 minus 1, which becomes a minus 6. Now that ends up being a polynomial. And so for domain purposes, anytime I have a polynomial, there's not a number I can't square, add the same number, and then subtract 6 from that. Therefore, my domain is all real numbers. Okay, and please express that in interval notation because I think they will ask you to do that as well. Alright, so let's try this guy. With f of x, or f minus g of x, that means we're going to just subtract those two functions that we are given. And this time, again, I'm going to write it with parentheses because now when I have this going on with this minus, that means I must distribute that negative through. You have to make sure you change the sign of the second term when you are subtracting. So I get a minus x squared and then a plus 1. Now I'm ready to go with combining like terms. So I'm going to start with this guy here to where I'm going to start with my highest power and go down. So it'd be a minus x squared. Come over here with my plus x again. Then I have a minus 5 plus 1 gives me a minus 4. Now, this is the f of x minus g of x. That's the difference. This part over here is the sum of those two functions, but we also have to determine what is the domain of this difference. So coming back here, this is a polynomial. There's no number we can't throw in there. Therefore, we have an all real number domain again. Okay? All right, let's try f times g. Let's scoot this up a little bit. That, by definition, tells me that I need to do f of x times g of x. So now I'm going to multiply the two functions together, and I get x minus 5 times an x squared minus 1, and hopefully you recognize this as FOIL. F-O-I-L is what we need to do here when we multiply two binomials together. So if I do x times x squared, I get x cubed. Then the outside term is a minus x. The inside term is a minus 5x squared. And the last term becomes a plus 5. And so this is kind of out of order. If we want to write it in our descending order, we can as an x squared minus the 5x squared minus x plus 5. But that will work as well. Can't combine anything together. It is another polynomial. Therefore, nothing to worry about in our domain. Everything is possible in all reals. Okay? All right. Now, f of x and g of x, now that we're going to divide together, f of x over g of x. A lot of times there's not too much simplifying that you can do on these division ones, but the helpful part of this is where our domain's going to change a little bit. Okay, it's not going to be all reals this time. We have to now worry about where this is going to be equal to 0 and exclude it. All right, so if I throw in f of x, that is my x minus 5, over my g of x, which is my x squared minus 1. And that actually is our answer. That, if you look at this guy right here, we could go one step further to help us out with our domain. How do I factor this x squared minus 1? Because it is a possibility that things may cancel top and bottom. Let's see. I'm just going to rewrite the top as an x minus 5. And then this, if you hopefully recognize as a difference of squares, and I factor into two binomials, they have to be exactly the same. One has to be a plus, the other has to be a minus. I'm going to split my x squared as x and x. And what do I square to give me a 1? It is a 1 and 1. So that is it completely factored. Notice nothing is exactly the same as the expressions, so you cannot cancel anything. Therefore, either one of these would be acceptable as our f over g. But the second one there is going to be very, very helpful whenever we are finding our domain. So this is a rational function that the denominator cannot equal 0. Well, ask yourself, what makes that 0? What makes that 0? So on the first one here, x cannot equal negative 1, and on this one, x cannot equal positive 1. So this is where we have to skip over on the number line those two numbers. So if we start at negative infinity and stop at negative 1, then I'm going to parentheses around everything, union from negative 1 to the next number, which is positive 1, and then I'm going to keep going from 1 to infinity, and that's going to give me my interval notation domain for this function. Okay, so always look at the domain after the fact to make sure that you exclude any numbers that make that denominator 0. Okay, all right, very good. We are halfway through this little section here. The next thing we're going to get away from is not the algebra functions this time of add, subtract, multiply, and divide. We're going to create a new operation function, which is called the composition of a function. So I'm going to give you the definition of it here. The composition of the function f and g. Now this symbolization is going to be very, very close to product. But you have to make sure that you do an open circle and not a closed circle for the multiplication. Kind of looks like fog. Sometimes you call it the fog function. So it is defined by this. So f composed with g of x, that's the way we read that, is defined to be f of g of x. So that looks really strange. Let me kind of separate that out for you. This function is inside of f. So what we're going to do is we're going to take that g function and replace it into the f function when we get ready to actually find these compositions, okay? So the domain of a composition function is the set of all x such that x is in the domain of g and g of x, all of those numbers on the inside, is in the domain of f, okay? So this is one where we're kind of work ourselves from the inside out, is what I say. We go to the inside and we put that in there and then work on the outside, okay? All right, we're going to kind of do the first part first here. That's a little bit more difficult when just finding the composition in terms of x versus when we look at the numbers. So let's look at f composed with g here. This, by definition, is f of g of x. Now, what I recommend is that you go to that g function first. There it is, x squared minus x minus 1. I'm going to take out this g of x and replace it with what it's equal to. So it looks like this. Now I get down to f of x squared minus x minus 1. So, just like when we had function notation where I had a number inside here that I had to place into that function, I now need to take all of this and replace any x in my f function with all of this. So we're going to replace x in f with x squared minus x minus 1. So what does the f function tell me to do? It says to take 5 times what's inside here and then add 6. Remember, it's just a rule. So just think of it as a rule. 5 times whatever's inside here, then add 6. So this is what I get, but this is not completely simplified because I can distribute that 5 through, which looks like this. 5x squared minus 5x minus 5. Then I'm going to add 6. So the only two things I can combine together here are the constants. And we get a plus 1 at the end. Now, does it ask me for the domain? If it would have asked me for the domain here would be all real numbers. Okay, because we're working with polynomials. That's really nice. Now, I've switched the order here. So by definition, this means that I need to do g of f of x. And in a sense, we're kind of going backwards here. So again, go to your f of x function. Let me change some colors here. Go to our f of x function, and I'm going to take this and I'm going to put it inside there. So it looks like this, g of now 5x plus 6. So now we have to compose again. We have to operate again, where now I'm going to take this and put it inside the g function. So here we go. Wherever I see my x, I'm going to replace it with 5x plus 6. So my rule of function g says I need to square what's inside here. So we're going to go 5x plus 6 quantity squared. Then subtract what's inside there. And then I'm going to subtract 1. And that right now is a valid answer, but it's probably not going to be taken by my lab math until we square everything and distribute things through and simplify, okay? So they want a simplified version of that. Now, here's the case where I have to FOIL this if I don't remember. So I'm replacing that to look at the first term, the outside term, the inside term, and the last. Do not just square 5x and square 36. You're missing the middle term. So the first term here, 5x times 5x is 25x squared. Outside, 5x times a 6 is a plus 30x. Inside is a 6 times a 5x, which gives me another 30x. And the last term there, 6 times 6 gives me a 36. So that is just this 5x plus 6 squared. Now, I have a minus here that I need to distribute through to this binomial. So I need a minus 5x minus 6, and then I get my minus 1. Okay, don't forget about that minus 1. All right, so let's simplify, and I think we're done. Here I only have 1x squared, so I'm going to go 25x squared. Then I have 30x plus 30x minus 5x. So that gives me a 55x. And then I have a 36 and a minus 6 and a minus 1. So 36 minus 6 is 30, minus 1 is a 29. So this new function becomes a 25x squared plus 55x plus 29. And so that would be our final answer. All right, very good. Now let's kind of go to, I think, the easier of the two. We could actually, if we wanted to, now take this and plug it into what we found for f of g of x, but we're gonna kind of just work with the numbers inside our functions, okay? So by definition, f of g of -1 means I have f of g of -1. I'm going to start from the inside, so I'm going to start right here, and I'm going to place that -1 into the g function and figure out what number that I get out whenever I plug in -1 in for all those x's. So I'm going to keep my f here, so I remember that I still have that piece, but I'm going to now replace -1 into each one of those x's. So I get -1 squared minus a -1 and minus 1. So again, I've taken that -1, placed it here, and I get this part right here. That's a parenthesis. All right, so what is that? -1 squared gives me a 1. Negative of -1 gives me a plus 1, and then I have a minus 1. So in the end, all of that operation comes down to just a positive 1. So what now I have to do is take that number that I get from g of -1, which is 1, and plug it into the f function, which is over here. That means I'm going to replace this x with a -1, or I'm sorry, a positive 1. So that means I'm going to take 5 times 1 and then add 6 to that. And now we get to simplify. 5 times 1 is 5, plus 6 gives me an 11, and that is our answer. Okay, now let's try it with this g of f of 2. that means by definition we have g of f of 2. I'm going to start from the inside function and take 2 and put it into the f function. So we're going to start right here. I'm going to rewrite the g so I don't forget it. Take 2 into f. So that means I'm going to take 5 times 2 plus 6. So 5 times 2 plus 6 is what I need to figure out. And when I do that, 5 times 2 by order of operations is 10, plus 6 is 16. So now what I need to figure out is what is g of 16. So you're evaluating two different functions, but you're doing it twice. You're doing it one time and then you're doing it again with another number. So I'm going to take 16 and put it into the g function, which means it's over here. It tells me I need to do 16 squared minus 16 minus 1. So this is 16 squared minus 16 minus 1. So by order of operations, we must square that number first, which is actually a 256. Minus 16 is a 240. Minus 1 gives us 239 for our final answer. Okay, so sometimes they might be big. That's okay. Other times they might be negative. That's okay too. But in the end, we can now compose functions. All right, now what about decomposing functions? That's kind of going backwards. And so let's see if we can go backwards and define two original functions given the composition. Now I will tell you that there could be multiple answers here on these types of problems depending on what's given to you. But we are given this h function and we have to determine what f and g are. Okay, so we're going to, h is equal to, if I have f composed with g, that means I have f of g of x. Now, the easiest thing for me to describe this as is you want the inside function, so in this case the g function, to be the expression. So the expression is the multiple terms inside that function. So in this case, I have an expression here of 2x squared minus 3. On the outside piece, I have a fifth, a power of 5. So if I let g of x equal the expression, so the inside function has to be equal to the expression, and then my outside function, if I take that expression out and put an x back in, the overall operation on the outside piece there is that fifth. So I have x to the fifth. So if you think about it, if I take that g function and put it into the f function, if I take this g function and I put it in right there, take out the x and put that in, I get exactly what I started with there, okay? So express h of x to the f of g of x. So these are my two functions, and so this would be my final answer on that, okay? Separating it out to find f and g. We now want to express that same function. Here I have f of g of x again. H is equal to f of g of x. And I will tell you that the easiest thing to do is to make sure that you let the inside function be the expression. So I'm going to let g of x equal that x squared plus 5, and then that f of x is left to the outside operation function, and in this case it's a square root. So I have the square root of what? Well, take this out and replace it with just an x. So looking at what we have here, does it work? If I take this and I plug it in for this x, take that x out and replace it with x squared plus 5, I do get exactly what I started with. And so those are our two functions when we're decomposing a composed function out. All right, so hopefully, I mean, that's not too difficult. It's just something, sometimes if you can't see it, then it gets hard. Okay, all right, now let's look at how do we determine function values from a graph and then be able to operate with them on that. And this can be tricky. You just have to kind of, number one, keep straight of what function is the g function and what function is the f function, okay? So we have some compositions and some operations here. So let's remind ourselves, if I am summing two values, that means that's the same as doing f of negative 3 plus g of negative 3. So I can separate them out from each other. Same way here with this subtraction, I can do f of 2 minus g of 2. So now the issue is we have to figure out, well, what is f of negative 3? What is g of negative 3? So that means I needed to find the y value when x equals negative 3. So I'm going to go to where x equals negative 3, which is right here. I need to figure out, now this is on the f function, which is the blue function. I now need to go up and determine the y value at that point. So remember, this is the point negative 3, 4. What I'm looking for, what is the function value at negative 3? That's the y value that I'm looking at. So this can be replaced with a 4. Now I'm looking for g of negative 3. So I'm going to negative 3. And I now need to go to the g function, which is the red function here. This is the point negative 3, 1. What is the y value on the g function at x equaling negative 3? It is 1. Therefore, simply adding 4 plus 1 gives me a 5. F plus g of negative 3 is going to be 5. Okay, let's try it again for 2. I need to find out what f of 2 is. So we're coming over here to x equaling 2, which is right here. The f function is the blue function, so it's right here, down here. This is the point 2, negative 1. Therefore, f of 2, what is the y value when x equals 2 is negative 1. That I now want to subtract the g value when x equals 2. Here's my x-axis when x equals 2. On my g function, that is the point 2, 1. So the y value when x equals 2 on the g function is 1. When I now do negative 1 minus 1, I do get negative 2. And that's my final answer there. Okay? All right. Now we're just going to compose our functions here. This is defined to be f of g of negative 4. And part D is defined to be, remember, the order matters, g of f of 3. We are now going to determine that. So we have to do things twice here, but we're going to compose, okay? So here, I'm going to figure out, first off, go from the inside out. Let me erase these off of here. I want to find when x equals negative 4 on the g function. So on my x-axis, negative 4 is right here. It is actually on the g function right there. So this is negative 4, 0. Okay, so that's negative 4, 0. Therefore, g of negative 4, what's the y value when x equals negative 4 on g? It is 0. So this brings me down to f of 0. So now I need to not go to a different x value when x equals 0, which is right here. On the f function, which is the blue function, I come up here. That is at 2. So f of 0 equals 2. And that would be our final answer there. So again, it's not that it's difficult. You just have to know which order and which function to look at. Let's look at this guy here. G of f of 3. I now need to find f of 3. So I'm coming over here to when x equals 3, which is right here. On the f function, which is the blue function, is down here at y equals negative 3. So now I need to figure out what is negative 3 on the g function. So I'm going to x equaling negative 3, which is right here. On the red function, which is right here, that's the point negative 3, 1. Therefore, the y value when x equals negative 3 is 1. And my whole composition there is equal to 1. Okay? All right, very good. That's all we have for compositions of functions and for the operations of functions algebraically with add, subtract, multiply, and divide, and a little tip of domain there on all of those. So please make sure you practice your work so you can master that, and we can move on to the next section, which probably will build somehow onto that. So until next time.